Let's take a look at more complex mechanism with a couple of bodies. What is given is the omega 5-1. 5 with respect to 1 is rotation, and it's a cam mechanism. So between 4 and 5, between those bodies, we have a general joint. So we will use the method of the supplementary mechanism. We will add a new body number 6 that is connecting 4 and 5 via rotational joints. So we will rewrite this mechanism, and we will use the general planar motion approach to find out the velocities and acceleration of point y. So the basic equation for velocities, velocity of the y point is velocity of the reference, that is velocity of point x, plus rotation of y around x, and for particular vectors we know the directions, and for vx we also know the magnitude. So vx is perpendicular to body number 5, and its magnitude is omega 5-1, which is given times the distance between point x and 051, the center of rotation. And we will solve this equation graphically or numerically. So this way we will find out the velocity of point y, which is at both at the body number 6 and body number 4. Now we will continue with body number 3 that is performing a combined motion. So we will write down the symbolic equations for 3 with respect to 1, and that is connected to the frame via body number 4 and number 2. In point Z, 3, 4, motion is 0, so we can rewrite the equation and solve it as usual. So in Z, V32 plus VZ21 is equal to VZ41. And we will solve this equation for VZ41. We know the both direction and the magnitude because we know how body number 4 is moving. So graphically, we know its motion in point y, and we can transfer that motion to point z, or we can calculate it numerically by finding omega 4-1, the angular velocity of body number 4 with respect to the frame, and we can get it from the velocity in point y and recalculate it for the point z. So both possibilities are valid. So what we have to do now is just to solve the equation, the vector equation. So we know 4-1 completely, and for 2-1 and 3-2 we know directions, and the arrows come from the vector equation. So what we are looking for finally is the omega 2-1, which we can calculate from the velocity of point z in body number 2 with respect to the frame. So the omega 2-1 is the velocity magnitude divided by the distance from point z to the center of rotation. So now we are done with velocities, and we can calculate the accelerations. So for accelerations, for the first part, we will start using the same vector equation. However, point y is performing rotation, therefore it's got both normal and tangent component. So normal component is calculated as a square of the velocity divided by the distance, and for tangent we know the direction. For the point x, the reference, we know that we know velocity, therefore we know the normal component magnitude, and the tangent is equal to 0 because omega 5-1 was constant. And for y, rotation y around x, again, we can calculate the normal component as velocity squared divided by the distance. And for the tangent component, we know the direction. So all we have to do now is to solve the actual equation. So we will put all the vectors that we know completely in there, and then the directions of the vectors for which we do not know the magnitudes. That would be AYX tangent and AY tangent. So we will put them together to get a solution. And here we go. So the important part now is the acceleration of point y, the tangent component, because that will give us, for the next steps, it will give us the alpha component of 4, 1. So we will now continue with the combined motion, and again 3 with respect to 2, that is that only has one component because it's translation. 2 with respect to 1, we know normal component, it's both direction and the magnitude, and for tangent component we know the direction, which is perpendicular. For Coriolis we can calculate it by 2 omega carrying omega 21 times v relative, that is v32. And for 1 we know completely because we know a motion of 4 with respect to 1 in point y, so we can transfer that into point z, and we can either do it one component at a time, or we can do it all together. So in here we do one component at a time, first normal and then the tangent component. Because we know the distance from the center of rotation and we know the magnitude of AY tangent, then we just recalculate it accordingly. Or we can calculate it numerically using alpha for 1 and then calculating A for 1 in point Z by multiplying it with the distance from the center of rotation. The Coriolis, it's 2 omega carrying 2 omega 21 times V relative, that would be VZ3 2. And again, we can, because it's a planar two-dimensional task, we simply multiply the magnitudes. As for direction, we take the relative velocity and we turn it 90 degrees in the direction of omega carrying. And well, we are getting close, because now all we have to do is to solve the vector equation. In here we are solving it graphically. So we put all the vectors that we know completely into the drawing, and then we add those two that we know directions only. That would be AZ32 tangent and A21Z tangent. Where the arrows are, it goes from the actual equation, vector equation. So now we know the acceleration of point Z on body number 2, and what we are looking for is alpha 2, 1. So if we know the tangent component in point Z, then we can calculate alpha 2, 1 by dividing this acceleration by the distance from point Z to the center of rotation, that is O21. And that's it, non-trivial example solved and hopefully explained.